Hello everyone and welcome to task number 5. In this task, we will understand the theory and intuition behind a type of artificial neural networks known as convolutional neural networks. And we're also gonna cover a type as well, kind of state-of-the-art artificial neural networks is known as ResNets or residual neural networks. And they actually, these are really powerful, deep neural networks that we can use, and you can actually apply them in any application. And I'm going to show you guys today how these neural networks are really powerful and how complex they are, and how we can actually build them in like a couple of minutes, which is super powerful. Okay, so if you guys remember in the previous task, in task number 4, we have been able to create our data generator, and we created 3 different groups of images. We had our training data, we had our validation data, and we had our testing data as well. Okay, so here, guys, I'm assuming that you have basic knowledge of artificial neural networks. And what we're trying to do here is we try to mimic the human brain. So our brain has hundreds of billions of neurons that communicate with each other with electrical and chemical signals. And it helps humans see, think, create ideas, even like me right now. Teaching, for example, is again, all that happening, because of all the neurons communicating in the brain. And what we're trying to do when it comes to artificial intelligence is that we try to mimic that mathematically. We just try to come up with just a couple of equations that try to mimic what's actually happening in our human brain. So this is a type of artificial neural networks known as convolutional neural networks. And simply, convolutional neural networks work really well with images. So for example, here we have our training data. So we have an image of, let's say, a mild case. And what we have here in the output is one of the 5 different classes. Maybe we have mild, we have, let's say, no DR, we have moderate, and so on. Here we have a dense, fully connected artificial neural network. Basically, here I have a lot of neurons that are organized in a certain fashion. We have the input layer, we have a hidden layer, and then we have the output layer. And we call it dense because all the different neurons in one layer are fully connected to all the neurons in the subsequent layer, okay? And what we have here, what we do when it comes to convolutional neural networks, is that we take in an image, we feed it in, we apply what we call it convolutions. Think of it as kind of, like a feature extraction. We try to extract the important features only from the image. And then once we create these feature maps, we call them, we do what we call it pooling. And think of pooling as a way of trying to reduce the size of the feature maps, to kind of compress the feature maps. So you guys will notice that here the size of these feature maps are smaller than this one because we have done pooling, or what we call it downsampling. And then once we have these pooled, essentially, feature maps, we do what we call it flattening. So we take all these pixels, the 2D, we make them in 1D here, and then we feed them as an input to our dense, fully connected artificial neural networks. And that's simply convolutional neural networks in like a couple of minutes. Please know that there are a lot of details in the background. There's a lot of, like math behind it, but that's from a very high level what we do. And that's what I want you guys to know, because in this task, or I would say in this entire project, I just want to show you guys the practical application. How can we actually build that without going in depth of, like what's the theory behind it, what's actually going on. I just want you guys to know the intuition and from a very high level how it works. We take in the image, we extract features from these images, we reduce the size of these feature maps with pooling, and then we flatten them up, and then we feed them to a dense, fully connected artificial neural networks. And I actually have a really powerful here visualization. I call it CNN in action. So if you guys go to this link, I have it open here separately. You guys will be able to see here, this is already a trained convolutional neural network to classify different numbers. So for example, here I can go ahead and write, let's say, number 5, for example, here. So I'm writing number 5. And as you guys can see here, the network actually told me that the first guess is 5. And you should be able to see here all the different layers. So for example, here I have this is the input. Here I have the first convolution layer. And if you guys can go here, you can show it. and you can hide it if you want. So these are the different convolution layers, followed by a downsampling layer 1. So if you can show it, you can hide it. So here I have my downsampling layers, and you guys notice that the size here has been reduced compared to this one. And then, because it's a deep neural network, here we have an additional convolution layer. So I have another convolution followed by another downsampling, and then we take all these pixels and then we flatten them up. So here I have my dense, fully connected artificial neural networks. And then here the output is one of the 10 outputs that I have, which is simply numbers from 0 to 9. And here the network told me already that the first guess was 5, which is pretty powerful. Okay, so what I'm going to do here next is I'm going to use a certain type of convolutional neural networks known as ResNets, or residual neural networks. And the idea here came from the following, is that if we wanted to build a really complex brain, that means we need to add a lot of layers. That means we need to have multiple layers, multiple hidden layers, multiple convolution layers. And one of the problems is that when you increase the number of layers in a convolutional neural networks, we found that there is an issue known as the vanishing gradient problem that tend to occur. Simply, you will find that when we actually train the artificial neural networks, we actually propagate the gradient information back to the network to try to essentially train it, to try to update the values of weights. Simply put, when we add a lot of these layers stacked on top of each other, we found that the gradient becomes very, very small. So we actually suffer from what we call the vanishing gradient problem. So we simply put, the performance of the network will be very poor if we add or stack up a lot of CNN layers back to back. That's all it is. So to overcome this issue, we do what we call it, or create what we call it, skip connection. So simply, we have our input here fed to a weight layer, followed by another weight layer here. And what we do is we add what we call it an identity mapping or skip connection. So we actually feed in the input as is, as you guys can see here. And then we add it up to whatever is coming out from all these different convolution layers. It's a very simple, I would say, trick, but by doing so, you will be able to actually train a really deep neural network, maybe like 200 layers or so, and you will not gonna suffer from the vanishing gradient problem. And ResNets are actually extremely powerful type of networks. And they have been extensively used, and they have achieved an incredible performance on what we call it the ImageNet dataset. The ImageNet dataset contains actually 11 million images, and counting. I believe right now we reach around 14 million images as we speak. And these are categories of all the different, I would say, images like out there with all the different classes. And the neural network, actually, we have a quick mini challenge coming up for you guys to do external research. I want you guys to tell me what is the performance of ResNets on the ImageNet dataset. But that's, again, I need to cover what's ResNets first before you guys go to the mini challenge. Okay, so the type of network that we're going to build here in this project is type of residual neural network as well, but we call it ResNet 18 model. And this is kind of the architecture of the network. Please note that there's a lot of, again, details. I just wanted you guys to understand from a very high level what's happening, because in the next task, we're going to go ahead and build all these different networks. So first, we feed in the input. We go through multiple layers. We go through zero padding. Then we apply convolution 2D. That's a convolution layer. We apply what we call a batch normalization. And then we feed it into a ReLU activation function. And ReLU stands for rectified linear unit activation function. And it introduces some nonlinearity to my network. And it's really powerful. And then we do max pooling 2D to reduce the dimensions. And afterwards, we add a series of res block or residual blocks. So here I have res block, res block, res block, and so on. And then we do average pooling 2D. We flatten it up. And then we add the dense, fully connected artificial neural networks. And this is simply the network on its own. Okay. And actually, again, we're going to build it from scratch in the next lecture. But please note that each of these blocks, like only the res block here, has something in it too. So if you guys can open the res block, that's what we have in here. So each of these blocks is actually a series of blocks as well in it. So the REST block itself has a convolution block first, followed by two identity blocks. So the question is, what's in the convolution block and what's in the identity blocks? Well, that's what we have in the next slide. So each of these convolution blocks is what we got in here. Simply, we feed in the input to the main path. So here I have the main path, and here I have the short path. In the main path, we go through conv2d, max pooling, batch normalization, and ReLU, and then another convolution2d, batch normalization, ReLU, another conv2d, and then batch normalization. And then here I have what we call the short path, and here we have conv2d, max pooling, batch norm. We sum up whatever we're getting from these two different paths, and then we apply ReLU, and that will be just a single block that we have in here, which is each of these REST blocks are captured in here. Okay, so actually it's a huge network essentially. Okay, what about the two identity blocks? That's what we have in here. So the identity block, and that's why we call it identity, because we can feed in the input as is to the short path, and then we add it up to whatever we're getting from here. So here we have conv2d, batch norm, conv, batch norm, and so on, and then we sum them up, apply ReLU activation function, and that simply summarizes our residual neural network. And again, please note that we're going to build it from scratch in the next lecture. But now it's time for mini challenge number 4. What I want you guys to do is to tell me what is the performance of ResNets on the ImageNet dataset. So please go ahead, do a quick Google search, and I will see you guys after the challenge. All right, hope you guys were able to figure out the challenge. Actually, the error is around 3.6%, which is, again, pretty powerful. So the error is approximately around 3.6%. You guys, again, can look it up, and you will find that ResNets are actually they provide a dramatic improvement over other older type of networks like AlexNet and some of the other 2012 or maybe earlier type networks. Okay, all right. So that's all I have for this task. I hope you guys enjoyed it, and see you in the next task.